Let's take a look now at section 6.3 and talk about operations on matrices. Up until now, we've seen matrices as a tool for solving systems of linear equations. We can take a system of linear equations and write it as an augmented matrix. We can then use that augmented matrix to organize our steps using row operations to reduce the matrix into row echelon form, and then use that to solve our system of equations. But matrices themselves can be used on their own as mathematical objects. We can think of them as other mathematical objects, for example, like numbers or variables. They don't work exactly the same way, though, but they are similar in many respects. Just like you can add and subtract numbers, and you can multiply and divide variables, we'll be able to do similar things to matrices because they will be objects the same way numbers and variables are mathematical objects. So how do we do that? How do we add, subtract, multiply, divide matrices? What does that even mean? So before we start with that, we have to begin by talking about the order of a matrix. All right? So every matrix is made up of rows and columns. So for example, here is a matrix that has 3 rows, 1, 2, 3. And it's going to have some elements inside. I'm going to write down 1, 2, 3, 4, 5, 6. So this matrix has 6 different items inside of it. The items inside of a matrix are called its elements. So here this matrix has 6 elements. Let me draw a different matrix which also has 6 elements. In fact, let me use the same elements. 1, 2, 3, 4, 5, 6. So this matrix also has 6 elements in it. And yet somehow, even though they both have the same number of elements, even though both of them have the same elements inside, both of them have 1, 2, 3, 4, 5, 6, there's clearly something different between these matrices. So here, what we're going to do is we're going to talk about a matrix depending on the number of rows and columns. Even if they have all the same elements, they're still not the same. And what sets these apart is this one has 3 rows and 2 columns, whereas this has 2 rows and 3 columns. This is called the order of a matrix. So the order of a matrix is given by the number of rows by the number of columns. If you have the number of rows by the number of columns, notice if you actually multiply those numbers together, it will give you the number of elements. Now, when we say this, number of rows by number of columns, make sure it's in this order. What I mean by that is here, this has 3 rows. So that's the first number we're going to write. This is called a 3. This has 1, 2 columns. So this is called a 3 by 2 matrix. This is its order. The order of the matrix is 3 by 2. On the other hand, this one has 2 rows, the top one and the bottom one, and it has 3 columns, the one on the left, the one in the middle, and the one on the right. So this is a 2 by 3 matrix. Notice 3 times 2 and 2 times 3 is 6 either way. So these two would have the same number of elements, but they'd be organized differently. This would be in 2 different rows and 2 different columns and 3 different rows. All right? Whenever you look at a matrix, you can talk about the individual elements inside, and you can distinguish them by their location. So here, let's draw a different matrix. Let's say this matrix is the matrix 2, 3, 4, 3, 2, 4, like that. Okay. So here I have a 2 by 3 matrix. A 3 by 2 matrix. It has 3 rows and 2 columns. All right. Here, this is row number 1. This is row number 2. And this is row number 3. Just like we had row operations in a previous section, the top row, the middle row, the bottom row. We've been calling these rows, and these are columns. Rows are named from the top down. columns are named from the left to the right. So this is column number 1, and this is column number 2. Hence, number 2. Hence, it's order 3 by 2. And it's always in that order, 3 by 2. All right. Now, let's say I wanted to call your attention to one of the elements of this matrix. And I said, I want you to look at the number 3. You say, well, there's a couple of those. Which one do you want me to look at? Well, one thing I could do is I come over here and I could circle it, right? Or I could point to it. But what if I wasn't there with you? What if I'm trying to get you to read this in a book or in some notes or whatever? So how do I distinguish this from this? How can I tell these two apart? Well, whenever we're talking about an element of a matrix, we can talk about it based on its location. Just like this is always given by the number of rows, and this is always given by the number of columns, the position of each element of a matrix will be given the same way. So here, let's say I wanted to draw your attention to this number 3. Okay? Well, first I would have to tell you which matrix it's in. And you'd say, well, it's in that matrix, right? Well, yeah, but remember, we have a few different matrices floating around on the same page. Okay, so one thing I could do, again, I could point to it. I could say, I want this matrix, or I could circle this one. But again, we're trying to find a way of writing this out so that we don't have to actually point to something. We want to be able to have a notation that without anyone being there to point at the right one, you should still know which one we're talking about. So whenever we're talking about matrices, just like when we talk about variables, we give them a letter. With matrices, we're going to go ahead and label them the same way. Here, I'm going to give this matrix a letter. And I'm going to call this the matrix capital M. I'll call this one the matrix capital N. And I'll call this one the matrix capital P. There's nothing special about these letters. However, traditionally, whenever you name a matrix, you use a capital letter. Capital A, capital B, capital C. Whenever you have a lowercase letter, little x, little y, little z, if you have a lowercase letter, that traditionally means you're looking at a variable. If you have a capital letter, traditionally that means you're looking at a matrix. You could use any letter you like. It doesn't even have to be a letter. You can use a symbol. You could use a little heart here and a little smiley face. But again, in most books, you'll see it done this way. Capital letters are for matrices. Okay? So now, you say, okay, I want you to look at this number. Well, okay, I don't want to point to anything. I want to tell you which one. Okay, I want you to look at one of the elements of the matrix P. Okay, well now it's a little more obvious. I'm looking at something from this matrix, because this is the matrix P. Okay, but the matrix P has a bunch of elements in it. So which one do I want? Well, I want this one. Okay, but without pointing. Oh, well, I want the one that's in the second row. Okay, we have a couple of numbers in the second row. But I want the one that's in the second row and the second column. Okay, there's only one number that's in all of those things. Out of all the numbers on this page, there's only one number that's in the matrix P, that's in the second row of matrix P, and in the second column. So this element right here would be labeled this way. It would be labeled P22. And you separate those with a comma, otherwise it looks like 22, right? This is the name of the matrix. This is which row it's in. And the second number tells you which column it's in. Okay. If I was looking at this element up here, this one would be labeled as N2, 3, because it's the element that's in the matrix N, so that's the first symbol, and then it's in the second row, first row, second row, okay, it's in the second row, and it's in the first, second, third column. So it's in matrix N, second row, third column. Just like that. Here, try that for just a second. I'm going to go ahead and say, here, try this element here. What would you label that element? Pause the video if you have to. Take a moment and label it. Whenever you're done, unpause the video and we'll give you the answer together. All right, and that's the element M2, 1. It's in matrix M. It's in row number 2. It's the second row. Top one is the first one. Middle one's the second one. And it's in the first column, the one all the way to the left. All right? So once we have this notation straight about how we label the elements of a matrix, and once we have this, when we can label the order of the matrix, it turns out that once you know both of these things, once you know how to classify matrices by order, and once you know how to label the elements of a matrix, the operations on matrices, addition, subtraction, multiplication, and division, as long as you know those two things, it makes a lot of sense what we're about to do. If you don't understand what order is, go back, maybe rewind the video or ask some questions about it, because if you can't keep this straight, the next few things that we'll see won't make a lot of sense. It'll be hard to tell what it is that we're doing. Okay, so let's go ahead and start off with the two easier operations, addition and subtraction. So let's talk about addition of matrices. For years, I didn't know how to spell matrices, and then Matrices. I don't know. That's the way I remember it. While we're at it, let's also talk about subtraction of matrices, because they are defined pretty much the same way. So let's begin with two matrices. And here I'll use the letters capital A and capital B for my matrices. Let capital A and capital B be matrices. These two matrices must be of the same order. So let A and B be matrices of order m by n. So these matrices both have that number of rows and that number of columns. Notice we don't have any specific numbers, so here it doesn't matter what our number of rows and what our number of columns are, as long as both matrices share that order. So if you have two matrices that don't have the same order, then we can't do this. You have to have the same order. Okay? If that's the case, then we can add matrices element by element. That is to say, let C be the sum of A and B. All right, so let's say C is what you get when you add A and B together. Okay, well, that's what we're defining. How do you add these things together? Or rather, how do you add these things together to get this? Well, let C be that sum. Then the element Cij, this might sound a little confusing at first. Don't worry. We'll come back and talk about what that notation means. It is similar to what we've had up here. But Cij is going to equal to Aij plus Bij. Likewise, if we let D be equal to A minus B, then the element Dij is going to equal to Dij will equal to the element Aij minus the element Bij. Just like that. Okay. So now that is the definition, but let's talk a little bit more about what that means. And the best way to do that, let's take a look at an example. All right, let's see. Example. Let's say I have two matrices. Okay, let's go ahead and add these two matrices together. Here's a matrix, 1, 5, 3, 7. And here's another matrix, 1, 2, 8, 5, 1, 2. All right, let's add those together. We can't. Well, why not? Because here, our definition, well, is that, I wouldn't even say our definition, just our technique. The way we add and subtract matrices begins by assuming that you have two matrices of the same order. Here, the order of this is 2 by 2. The order of this is 2 by 3. These cannot be added because they have a different order. And say, okay, so how do I fix that? You don't. Addition is not defined for these. Right? There are plenty of operations that we've had in the past that have not been defined. We don't define dividing by 0. We don't define the natural log of -1. We don't define lots of things. We don't define a bunch of numbers for the logarithms. Here, that's just another instance of here's something we don't define. We've never defined how to add two matrices if they don't have the same order. All right, so what if they do have the same order? Okay, so let's take a look at the next example here. Let's go ahead and add the two matrices 1, 2, 5, 3, negative 4, and 8. And to that, let's go ahead and add the matrix 5, 1, 2, negative 2, 1, 0. All right, so these do have the same order, so I should be able to add them. Whenever you add two matrices that have the same order, the answer will also have the same order. So if this has 2 rows and 3 columns, and this has 2 rows and 3 columns, then your answer will also have 2 rows and 3 columns. Okay. So now what are the 6 elements? I'm going to have 2 rows and 3 columns. 2 times 3 is 6. So I'm going to have 6 elements. Well, that's what this tells you. This tells you to find an element, ij, that's the same as adding the elements ij from the first matrix plus the element ij of the second matrix. Or in other words, right here, you want to find something that's in the first row and first column. Right? You want to find something that's in C11. Well, then add A11 plus B11. Oh, add these two that are in the same position. That's A, first row, first column. That's B, first row, first column. And if you add those, that'll give you C, first row, first column. And the same thing will happen for these two. This is A, 2, 1. Oh, sorry, I said that backwards. A1, 2. And that's B1, 2. And if I add those together, that'll be C1, 2. And that's A1, 3 and B1, 3. And if I add those together, that'll give me C1, 3. Notice all I'm doing is I'm adding the corresponding elements, the elements that are in the same spot. If I add these, 3 and negative 2, that'll give me 1. Negative 4 and 1, that's negative 3. And if I add 8 with 0, I get 8. Just like that. Subtraction, you notice, works the same way. To find the elements of the difference matrix, I'm just subtracting the 2 elements in the first 2 matrices that were in the same position. So for example, let's say we have the matrix 2, 5, 3, 1. And we're going to subtract the matrix 4, 7. All right. Go ahead and pause the video and subtract those. And if you, once you get an answer, go ahead and unpause and we'll go through it together. All right, and that's a trick question, obviously, yeah? Since these two have a different order, they cannot be subtracted. Addition and subtraction have the same kind of definition. We do them the same way. So here, these cannot be subtracted. Or you might say subtraction's undefined. Again, because they have a different order. All right. Okay, so now let's do one that's not a trick question. Here's a matrix 5, 3, 8, negative 2, negative 1, 6. From that, go ahead and subtract the matrix 3, 9, 2, negative 1, 5, and 5. So go ahead and pause the video and try that one. And once you get an answer, go ahead and unpause and we'll go through it together. All right, and to subtract, of course, these we can subtract because they do have the same order. This has 3 rows, 2 columns, 3 rows, and 2 columns. So we can subtract, and our answer will also have 3 rows and 2 columns. So to get the elements of this result, we're simply going to subtract the corresponding elements. So these two are in the same spot, first row, first column. So 5 minus 3 is 2. 3 minus 9 is negative 6. 8 minus 2 is positive 6. Careful, that's double negative. So negative 2 minus a minus 1. Well, that's negative 2 plus 1. That's negative 1. Negative 1 minus 5 is negative 6. And 6 minus 5 will give me 1. And there we go. That is our difference. Now, when we're looking at matrices, there's going to be one particular matrix that will show up from time to time. Sometimes you'll have a matrix which is made up of all zeros. So for example, this. Or you'll have a matrix that looks like this. Or maybe you'll even have a matrix that looks like this. These are called the zero matrix. You're saying, well, so they all have the same name, so are they equal to each other? Well, no. If you have two matrices that don't have the same order, then they're not equal to each other. So you say, well, if they're not equal, how come they're all given the same name? Well, they are all the zero matrix, but they're zero matrices of different dimensions. This is called the zero matrix of order 2 by 2. Or if you want to say it a little shorter, you can just say this is the 2 by 2 zero matrix. Same thing over here. This is the 2 by 3 zero matrix. 2 by 3 zero matrix. And this has 3 rows and 1 column, so this would be the 3 by 1 zero matrix. Both of these are accepted names. You can either say the 2 by 3 zero matrix or the zero matrix of order 2 by 3. The second one sounds a little more dramatic, right? This one sounds a little more dramatic, but they are equivalent. Either one's fine. So there's a few properties of matrices, which are going to sound really, really familiar. They're the same kind of properties that you're familiar with when you add and subtract numbers. So properties of addition and subtraction. Okay, let's begin with 3 matrices. I want to call them A, B, and C. Now, first of all, we need to make sure that they are all of the same order. So let A, B, and C be matrices of order m by n. It doesn't matter what their order is, but just like with our previous statement, we do have to have all of the matrices be of the same order. Doesn't matter what that order is, as long as they're all the same. And let 0 be the zero matrix of order m by n. Okay, so here this is not the number 0. It's a matrix made up of a bunch of zeros. And it happens to be the one that is of the same order as these first 3 matrices. As long as you have that, the following things are true. If you add A with B, that's the same as if you added B with A. Or in other words, just like with regular numbers, addition is commutative. If you add A first, then B, or if you add B first, then A, you get the same answer. Just like with numbers, 2 plus 3 is the same as 3 plus 2. Same thing for matrices. Addition is commutative. We also have associativity, meaning it doesn't matter what order I add things in. And it also doesn't matter how I group them. If I'm going to add A with B with C, I could do it either way. I could say, let me add together B and C first, and then let me add A. Or let me add A and B first, and then let me add C. All right. So you can group either these two and then that one, or these two and then that one, and it doesn't make a difference. So here, this is called commutativity, the same as it was with real numbers, and this is called associativity. The next one, if you have the difference of a matrix with itself, that's equal to the zero matrix. So just like with regular numbers, a number minus itself is 0. Here, these are matrix minus itself is the zero matrix. And finally, just like with real numbers, if you take a matrix and add 0, or in this case, the zero matrix, that's the same as if you took the zero matrix and added A, and that's just going to give you A. Or in other words, just like with real numbers, if you take a matrix and add 0, you just get what you started with. Right? If you add 0, nothing changes. Notice this is not the number 0. This is a matrix 0. We don't have a way of defining adding a matrix with a number, right? Because of course, if we're adding a matrix with a number, here that's a 2 by 3 matrix. A number is just a single number. And again, we don't have a way of defining that. The only thing we've defined is how to add or subtract matrices that have the same order. So here, if we tried to take, for example, this matrix and add the number 0, we don't have a way of defining that. That doesn't mean anything. Here we mean the 0 matrix. Right? So these are some properties that you recognize because they're all the same as with regular numbers. Here, if A was a number instead of a matrix, this would all still be true. Okay, so now let's take a look at the next type of operation. We've seen addition and subtraction, we've seen how to do it, and we've seen a few simple properties which look really familiar because they're the same kind of properties that we usually have for addition and subtraction. Let's take a look now at the next operation. Let's take a look now at multiplication. Let's talk about how to multiply things when we're talking about matrices. Now, multiplication is slightly more complicated. You say, oh, it's going to take longer to do or it's harder to do. Well, kind of, but that's not the only reason why it's complicated. Think about this for a second. Let's say I write these 3 things. Okay, I have 2 times 3, and I have 2 times 3, and I have 2 times 3. And obviously, that's the same answer every time. That's equal to 6, and that's equal to 6, and that's equal to 6, just like that. And it makes no difference which of these symbols I use. I can either write them together like this, or with a dot, or with a little cross. But have you ever wondered, why do I have different symbols? Well, part of the answer might just be, well, because mathematicians just felt like it. Some people like using one symbol, or some people like using the other symbol. But then think about addition and subtraction. There's only one symbol for addition, the plus sign. There's only one symbol for subtraction, that's the minus sign. And so why is this special? Why does this have so many different notations? It turns out that it's not that the multiplication symbols are different just because, but rather because there are different kinds of multiplication. Whenever you're dealing with just real numbers, if you multiply this way, or this way, it doesn't make a difference because there's only one way we have defined for multiplying just 2 regular real numbers. So yeah, okay, I could use a different symbol, but there's only one thing I could possibly mean. I mean 2 times 3, the same way we usually mean, right? Take 2, add 2, and add another 2. But now we're starting to look at things that are not just regular numbers. We're starting to look at things like matrices. So we're going to start to notice that there are different ways of defining multiplication. Anyone who takes math beyond college algebra, if you start going into trigonometry and calculus, and especially if you start taking application courses like physics, you'll start to notice that these 2 symbols are not interchangeable. This, in certain classes, is called the cross product. This is called the dot product and the scalar product. So in the further along you go in math and in applications of math, these start to take on a lot of meaning. For now, we're not going to go quite into all of that, but we are going to define 2 different ways of multiplying that involve matrices. The first one we're going to define is the nice one, and that's called the scalar multiple. That's the one we wish multiplication always looked like. So this is called the scalar multiple, or rather the scalar multiplication. Okay, scalar. What's a scalar? So when it comes to multiplying matrices, scalar means a regular real number. Here's what this would look like. Let's say you start off with a matrix 2, 3, 5, 7. All right, so that's a matrix. If we were going to multiply it by something, we could multiply it by one of 2 things. We could multiply it by another matrix. We'll get to that in a moment. Or we could multiply it times just a regular number. Now, before we said we don't define addition of matrices by a regular number. I wouldn't be able to say take this matrix and add to it the number 0 or add to it the number 5 or anything like that. But multiplication is different. We define a scalar multiple by taking the elements of our matrix and multiplying each of them by the scalar. All right. So here, let's write that. Let me write that out in a generic way. Let's say let A be a matrix. Notice I don't say anything about its order. This will be true of any matrix. It could be 1 by 1, 2 by 2, 7 by 55. It doesn't make any difference as long as you have a matrix. Let A be a matrix and let C be a scalar. When we say scalar, all we mean is a regular real number. Not a matrix, not an equation or a function, just a regular real number, like the number 5 we have here. Okay, then the scalar product written as CA. Traditionally, we write the scalar in front of the matrix, although technically you could write it in the back, but traditionally we write the scalar first. The scalar product CA has element CAIJ equal to C times AIJ. That looks a little strange here. What I mean by that is if you want the IJ element of the matrix CA, that's the same as taking the element of A and multiplying it times C. This is a formal way of saying it. What that'll look like is, okay, I have a 2 by 2 matrix. If I multiply it by a scalar, I'm going to get another 2 by 2 matrix. Now, if I want this element of the matrix, that's 1, 1, first row, first column, I'm going to come over here, take the element that's in that same position, first row, first column, and multiply that element times the scalar. And that will go here. If I want this number, this element, I'm going to take the element that's in that same spot and multiply it times the scalar. So 5 times 3 is 15. For this one, I will take 5 times 5 is 25. And for this one, I would take 5 times 7 is 35. Just like that. And that's called scalar multiplication. We're multiplying a matrix by a scalar. So here, try that for a moment. One thing about scalar multiplication that's nicer and a little bit simpler than addition or subtraction, it always works. You're not going to have a time where you say, oh, I can't multiply those, it's undefined or anything like that. This will be true of any matrix, and this will be true of any scalar. So let's say you have negative 2 times the matrix 1, 3, negative 4, 2, 0, 5. Pause the video, multiply that out, and when you get an answer, unpause and we'll go through it together. All right, so we have a matrix, 3 rows, 2 columns, 3 by 2. So the answer will be 3 by 2. And we're going to take each of these elements and one at a time multiply them by the scalar. So 1 times negative 2 is negative 2. 3 times negative 2 is negative 6. Negative 4 times negative 2 is positive 8. 2 times negative 2 is negative 4. 0 times anything is going to stay 0. And 5 times negative 2 is negative 10. And that is our scalar product. That's what we get when we multiply that matrix by that scalar. One thing to note is that our scalar can be any real number. It doesn't have to be a positive. It can be a negative. We could also use a fraction if we really want to, or if we really need to. Let's say, for example, we had the matrix 5, 2, 6, negative 8, 4, 0. And I'm going to go ahead and multiply by the scalar 1/2. just like that. Here, go ahead and pause the video and give it a try. And once you have an answer, go ahead and pause and we'll go through it together. So here, you're going to go ahead and simply take the elements of your original matrix and multiply them one at a time by 1/2. So here, 5 times 1/2, well, that's 5 halves. 2 times 1/2, that's 1. 6 times 1/2, that's 3. -8 times 1/2, that's -4. 4 times 1/2, that's 2. And 0 times 1/2, well, anything times 0 is going to stay 0. Just like that. Now, let's talk a little bit about the name of this. This is called scalar multiplication. This isn't something that's inherently mathematical. It's more of a physical interpretation. But I want you to consider the following. Think of this as a point, like 5, 2, 6, -8, and 4, 0. And think of those as 3 separate points. 1 point, 2 points, 3 points. Also, think of these as being 3 separate points. 1 point, 2 point, 3 point. 2, 0, 3, -4, 5 halves, 1. Now, I want you to take these 3 points and graph them, just like on the XY plane, and connect the dots. You're going to form a triangle. You're going to form a little shape. Do the same thing for these. Take these 3 points, graph them, and connect the dots. You can do them on the same graph. Once you're done, go ahead and unpause the video, and we'll go through it together. All right, so if you graph these right here, the 5, 2, 6, -8, and 4, 0, you're going to get this shape right here. All right, that's going to be 4, 0, that's going to be 6, -8, and that's going to be 5, 2. But now if you graph these sets of numbers right here, these points, if you graph 5 halves, 1, that's that number. If you graph 3, -4, that's that point right there. And if you graph 2, 0, that's that point right there. And if you compare the two illustrations, notice that they have the exact same shape. They're both, I don't know, like one's a bigger version than the other. So it's like if you took this one and then like made the same shape but made it grow, you scaled it up. Oh, hence the name, right? Here, the object remains the same, but its scale changes. You took the original one in blue, and when you multiply by 1/2, what you do is you scale it down to be half the original size. This is where the name's going to come from, the scalar multiplication. This is a physical interpretation of what's going on over here. This is not necessary for this, but it's a nice visual to help you remember exactly what that's, what's one interpretation of that. And it also helps to remember the name. When you're multiplying a matrix by a number, what you're doing is you're taking that and scaling it. You could try it with these as well. I'm not going to do those right now, but you could, and you'd see that this and this shape are going to be related, but different sizes. Same thing with this one. This one, if you create a shape by these points, multiplied by 5, you're going to notice that they're the same shape, but one's going to be 5 times bigger than the other. One's going to be twice as big as the other. And here, this one is half as big as the other, as you see there. Okay. All right, but that's not something we're going to worry too much about. It's just a visual to help us see another aspect of scale, what that means, scalar multiplication. But the other thing we want to look at now is the other kind of multiplication, and that's matrix multiplication. Here's how you multiply a matrix by a number, a scalar. How do you multiply a matrix by another matrix? All right, let's talk about that. So when you multiply two matrices together, you won't be able to just multiply any two matrices. Just like addition and subtraction, not every pair of matrices can be added or subtracted. It has to do with their order, with their number of rows and columns. Here, that didn't matter because we only had one matrix. This one doesn't have an order, doesn't have rows and columns. So here, we don't worry about that. Here, any matrix can be scaled. But matrix multiplication, it will matter what the order of our matrices. You say, oh, so just like with addition and subtraction, they have to have the same order. Not exactly. So here's how this is going to work. Let's say I have the matrix 1, 3, 2, 5, like this. And let's say I have the matrix, let's see here. Let's use 3. Oh, actually, let's do this. So 2, 1, 5, 4, 6, let's say 2, like that. So here, that's a 2 by 3 matrix. All right, these two matrices are not the same size, but that doesn't mean we cannot multiply them. Maybe we can, maybe we can't. You say, well, how do you check? Start by writing the order of the matrix, and make sure you keep these in the same order. Meaning, if this one's first, let's do this one first. So here, the order of this matrix, this has 2 rows and 2 columns. So this is a 2 by 2. Okay. Now this has 2 rows and 3 columns. So this is a 2 by 3. Now, how you can tell if the matrices can be multiplied or not is you look at these numbers. This is why it's important you leave this one on the left and this one on the right. Because here you're comparing the second number from the one on the left with the first number of the matrix on the right. If you switch them, then that's no longer the same set of numbers. So here, if these two are the same, we multiply. If they're not the same, if you have a 2 and a 3 or a 3 and a 5, or if they're anything different, if not, we cannot multiply. Okay. All right. Well, what about these? Do these tell us anything? Yeah. These will tell us the order of our answer. Because notice, we have two matrices that are of different order. So what's the answer going to be? Is it going to have the order of this one? Is it going to have the order of this one? Well, it depends. Sometimes it'll have the order of this one. Sometimes it'll have the order of this one. And other times it'll have an order that's completely different from either of these. This is how you can tell. This tells you the number of rows in your answer. Number of rows in the answer. This number right here tells you the number of columns in your answer. So what that means is that this matrix times this matrix, when you multiply those together, you're going to get a 2 by 3 matrix. Whenever you're going to multiply two matrices together, my suggestion is that you draw a blank matrix that has the right size. Because we're going to fill in that matrix, and there's a lot of information that's going to be happening here. So if you draw a blank matrix, you'll know if you're done once you fill it all in. If you don't draw a blank matrix first, it's really easy to accidentally forget to do one part of it. So here, I'm going to just rewrite this down. I'm going to write this over here so that we have extra space to work on. That's going to be 1, 3, 2, 5. And I'm going to multiply that times 3, 1, 5, 4, 6, 2. Just like that. And now when I multiply those two things together, I'm going to end up with a matrix that is 2 by 3. So what I'm going to do is I'm going to fill out a blank 2 by 3 matrix. And here I'm going to do that literally. I'm going to draw 3 blanks for my first row. And I'm going to draw 3 blanks for my second row. That way, if I fill all 6 of those spaces in, I know I'm done. If I don't fill in all 6 of them, well then I know something's wrong and I still need to finish. All right, so how do I fill these in? It depends on their position. So here, this is in row number 1, column number 1. Okay, so in order to fill this in, what I'm going to do is I'm going to go to row number 1 on the left. The rows are always going to come from the matrix on the left. The columns are always going to come from the matrix on the right. So if this is row 1, column 1, I'm going to come over here and I'm going to grab row number 1. Oh, sorry, row number 1. Top row. And I'm going to come over here and I'm going to grab column number 1. First column like that. Okay. And now I'm going to just multiply across and down and then add these together. So here, let me erase that. There we go. Want to keep that straight. Okay. So the way this is going to go is start from the left to the right, top to bottom. Take that 1 times that 3 and multiply them together. 1 times 3. Now, move over and move down. 3 times 4. You're going to multiply those together. And then once you've done this product and this product, you're going to add those answers together. So here that's 1 times 3 is 3. And 3 times 4 is 12. So 3 plus 12. Well, 12 plus 3, that's 15. So that's the first number in my product. I know this is going to seem a little strange, that pattern. There's a good reason why it's established that way, but it's not something we really talk about. Basically, it's done this way because it makes a bunch of other things work. A bunch of things in physics and math work out really nicely if we follow this pattern. Unfortunately, we don't see those things, so for us, it's just, okay, here's how you multiply, and it just looks a little weird. Okay, so now, let's talk about this spot. All right, well, that's in the first row, second column. Okay, so I'm going to come over here. Rows always come from the left, columns from the right. So I'm going to take row number 1 and column number 2. Row 1, column 2. And now I'm going to go left to right, top to bottom. It's going to be 1 times 1. Now I'm going to go to the right and down. 3 times 6. And once I've done those multiplications, I'm going to add. So here, that's going to be 1 plus 18 is 19. Okay. Let's take a look at another one here. Let's say this spot right here. Well, that's in row number 1, column number 3. Row 1, column 3. So grab the first row from the left and the third column from the right. And again, left to right, top to bottom. 1 times 5 makes 5. 3 times 2 makes 6. And then if I add those, 5 plus 6 makes 11. And that's the first 3 numbers. Now we got to do these down here. So at this point, pause the video and see if you can finish this off. See if you can find the other 3 numbers that should go right here. Pause the video, and once you have all 3 of them filled in, go ahead and unpause and we'll go through it together. All right, so this number right here is in position, it's second row, first column. So I'm going to grab the second row from the left, the first column from the right, and now I'm going to go left to right, top to bottom. So this will be 2 times 3. And then that'll be 5 times 4. Then I'm going to add those together. 2 times 3 is 6. 5 times 4 is 20. So 6 plus 20 will be 26. And that's that first number. Next, we're going to look at this spot here. That is in the that is in the second row, second column. So I'm going to take the second row from the left. And I'm going to take the second column from the right. And left to right, top to bottom. Here, 2 times 1. Here, 5 times 6, right? Left to right, top to bottom. 2 times 1. And then separately 5 times 6. And then I'm going to add those. So 30 plus 2 is 32. Just like that. And finally, we can do this row 2, column 3. So grab row 2 from the left, grab column 3 from the right, and then multiply left to right, top to bottom. So here we're going to take 2 times 5. Well, it's going to give me 10. And then I'm going to move to the right on this one. I'm going to move down on this one. 5 times 2 is also 10. And then when I add 10 with 10, I'm going to get 20. And there we go. If we multiply together the matrix 1, 3, 2, 5 with the matrix 3, 1, 5, 4, 6, 2, we get the matrix 15, 19, 11, 26, 32, 20. Just like that. Keep in mind, not every matrix can be multiplied. So for example, let's say I have the matrix 3, 5, 2, 1, 7, 8. And let's say I have the matrix 2, 3, 5, 0, negative 2, positive 4. And we were supposed to multiply these. That's not going to happen because this has 3 rows, 1, 2, 3. It has 2 columns, 1 and 2, and so it's a 3 by 2 matrix. This one is also the same dimension, 3 by 2. Since they're the same dimension, we would be able to add them. But that's not how we check for multiplication. Here, notice these are different. The number of columns here is different from the number of rows here. And because these are different, we cannot multiply. All right? Why can't we multiply if those are different? It comes down to that pattern we were following. Here you're going to go left to right, top to bottom. So here, let's say we're just trying to multiply the very first row with the very first column. Right? Left to right, top to bottom. Left to right, top to bottom. Okay, well that would be 3 times 2 is 6. Okay, and then I would move to the right. 5 times 5 is 25. Okay, and then I'd move and, oh, I'm out of numbers. So what happens is here, I run out of numbers before I run out of numbers here. So here, 3 times 2, okay, cool. 5 times 5, okay, nice. Negative 2 times a number that doesn't exist. Oh, yeah, I can't do that. It's not like I'm saying negative 2 times 0. It's not a 0 here. Because if there was a 0 here, we would have written it. No, there's no number here. So it's 2 times 3, 5 times 5, and negative 2 times a number that doesn't exist. Oh, that's meaningless. We don't know how to multiply by numbers if they don't exist. Okay, so then we can't multiply. Here we go. Let's take a look at another example. Let's say we have the matrix 1, 2, 2, 3. And let's say we're going to multiply that times the matrix 4, 1, let's say 3, 2. You can tell I work really hard for my examples, right? 1, 2, 3, 4. And we're also going to multiply together the matrix 4, 1, 3, 2 times the matrix 1, 2, 2, 3. Okay. Notice this is a 2 by 2 matrix. And this is a 2 by 2 matrix. And since these match, that means I can multiply. Okay. And not only can I multiply, but I know that my answer will have 2 rows and 2 columns. This number is always the number of rows. This number is always the number of columns. Okay, so I can go ahead and write that out. That's a 2 row, 2 column, and I'm going to just fill in an empty matrix. I have 1, 2, 3, and 4. Just like that. All right, so let's go ahead and fill that in. Row 1, column 1. Okay, row 1 from the left, column 1 from the right. 1 times 4, separately 2 times 3, and then add. 4 plus 6 will give me 10. Okay, the next one, first row, second column. Okay, so top row, second column, 1 times 1 separately, 2 times 2, and now add. That's 1 plus 4. Oh, that'll give me 5. The next one, second row, first column. Okay, get the second row here, the first column there, left to right, top to bottom, 2 times 4, and then separately, 3 times 2. All right, 1 times 4, 3 times 3. I saw the wrong number. 2 times 4 and 3 times 3. Well, that's going to be 8, and that's going to be 9. And if we add 8 and 9, we get 17. And finally, this is second row, second column. Okay, so second row from the left, second column from the right, left to right, top to bottom. 2 times 1 goes first, and then 3 times 2 goes second, and then you add. So 2 times 1 is 2, 3 times 2 is 6, and 6 plus 2 will give me 8. All right. So that gives us our matrix. If we multiply together 1, 2, 2, 3 with 4, 1, 3, 2, the answer is the 2 by 2 matrix 10, 5, 17, 8. Go ahead and try this one. Multiply these two together, and once you get an answer, go ahead and unpause the video and we go through it together. All right, so let's see here. Here, that's a 2 by 2 matrix, and so is that. And since these match, that means we will be able to multiply. And not only will we be able to multiply, we know our answer will have 2 rows and 2 columns. So here, let me fill in a blank 2 by 2 matrix. All right, so let's see here. That's going to be first row, first column. So I'm going to take the top row here and the left column. Left to right, top to bottom. 1 times 4 is 4. 1 times 2 is 2. And if I add those together, 4 plus 2 will give me 6. Okay. Let's take the next one. That's first row, second column. Okay, so first row here, second column there. 4 times 2 is 8. 1 times 3 is 3. And if you add 8 and 3, you're going to get 11. Let's take a look at the third one here. That's second row, first column. So take the second row here and the first column there. 3 times 1. 2 times 2. And if you add those, 3 plus 4 will give you 7. And finally, if you have this one here, second row, second column, you'll take the second row, you'll take the second column, 3 times 2, that's 6. 2 times 3, that's also 6. And if you add 6 with 6, you're going to get 12. Notice that these were the same matrices. 1, 2, 2, 3. 1, 2, 2, 3. 4, 1, 3, 2. 4, 1, 3, 2. But the difference here was that they were in a different order. Here I had this one on the left, whereas over here I had it on the right. And notice that my answers are completely different. Sure, they have the same number of elements, but all the elements are completely different. This is the first time that you've ever seen multiplication that is not commutative, meaning it matters what order things are multiplied in. So here, note, matrix multiplication is not commutative. This is the first time you've ever seen that. It might take a little bit of getting used to. Usually, if you have two things multiplied together, if you have 2 times 3, that's the same as 3 times 2. If you have x times y, that's the same as y times x. The order of multiplication doesn't usually matter. Matrices are the first time where you see that it does. There are other things where the order matters. You'll see those in later classes if you take classes beyond algebra. But for now, this is the first one you've ever seen, probably. Matrix multiplication is not commutative. If you multiply together the matrix A and B, you're not going to get the same as if you multiply the matrix B and A. So on your homework, on exams, and so forth, be very mindful of which order they're multiplied in. If you rewrite something, don't change their order. The order actually does matter, and it gives you very different looking answers. In some cases, changing the order will change the numbers of the matrix. In other cases, it'll even change whether or not the matrix can be multiplied together. So just be mindful of that. Matrix multiplication is not commutative. Addition and subtraction were, but not multiplication. And finally, the last thing for this section, let's do an example of what's called a matrix equation. Matrix equations can become very complicated, but here we're going to stick with a very nice, short, and simple. You are familiar with solving variable equations. Something like 2x plus 5 is equal to 12. All right? Right, something like that. And whenever you have a variable equation, you try to solve for the variable. So you get rid of all this other stuff. All right, so let me subtract 5 from both sides. That goes away. And that'll give me 2x equals 12 minus 5. Well, that's 7. And then I can divide both sides by 2. Like this. 2 divides 2 to give me just x. And I get x is equal to 7/2. Okay. Well, now let's talk about, so this is a variable equation. It's an equation that has a variable, and you're trying to solve for the variable. Well, remember, matrices are objects, mathematical objects, just like variables and numbers are. So just like we can have an equation with numbers and variables, we can have an equation with a matrix. So this is called a matrix equation. Let's say we have a couple of matrices. Let's say the matrix A is equal to 1, 6, 4, and negative 2. And let's say the matrix B is equal to 2, negative 4, 6, and 9. Just like that. And now, let's go ahead and solve the matrix equation. Let's solve the matrix equation 3x plus A is equal to B. Okay, well, that's actually pretty simple looking. It looks just like a variable equation, right? You're trying to solve for x. Okay, so that's not anything different. Just like up here, I got rid of my plus 5 with a minus 5. Here I can get rid of this plus A with a minus A. And whatever I do to one side, I do to the other side. All right, that's nice. So it'll give me 3x is equal to B minus A. And then I can get rid of that 3, and I can do that by dividing by 3 here. And I'm going to write it a slightly different way. I'm going to say I'm going to multiply by 1/3, which does mean the same thing. All right, dividing by a number is the same as multiplying by its reciprocal. And I'll do the same thing over here. I'll say, okay, I'm going to multiply both sides by 1/3. Now here I'm multiplying everything by 1/3, so let me put all that stuff in parentheses. But now 1/3 times 3 is 1, and that isolates my x to give me 1/3, and in parentheses, B minus A. And you say, well, that wasn't so hard. We solved for x. Well, yeah, but what is this? You say, well, it's 1/3 times B minus A. Yeah, but what is this? These are matrices. We should be able to find this. So let's go ahead and do that. Here we're going to subtract. Notice this is in parentheses, and just like with numbers and variables, parentheses go first. So here we're going to write this as x equals to 1/3 times, okay, so let's go ahead and subtract these. B minus A. Make sure you keep things in order. So that's B, that's A. So let's start subtracting. 2 minus 1, that's 1. Negative 4 minus 6, that's negative 10. 6 minus 4, that'll give me 2. Notice I'm taking B, subtracting A. And 9 minus a negative 2. No, minus a minus is plus, so 9 plus 2 is 11. But now we're going to take this matrix and we're going to multiply by this scalar. And when you multiply by a scalar, you simply multiply each element of your matrix by that scalar. So here, that's going to be 1/3 times 1, which is a third. That's 1/3 times -10, which is -10/3. 1/3 times 2 is 2/3. And 1/3 times 11 is 11/3. And there we go. We've solved the matrix equation. Notice that we organize it the same way we organize solving a variable equation. You isolate your x. But normally when you isolate an x in a variable equation, you get a number. Well, yeah, because all of these are numbers. But in a matrix equation, these aren't numbers, they're matrices. So you're going to do the same thing. You're going to isolate your x, but then once you've isolated your x, these matrices can still be added or subtracted as appropriate. Here it's subtraction because I use subtraction to get rid of that plus. So once you get to this point, you're not done yet, but you still need to simplify this. B minus A, okay, that gives me this matrix, but then don't forget you're multiplying that by the scalar 1/3, which gives you your matrix. So notice the solution to a variable equation, these are all numbers and your solution is a number. The solution to a matrix equation, all of these are matrices, and in the end, your solution is a matrix. And that is it for our section. If you guys have any questions, make sure you write them down and make sure you ask them during our class time or our office hours. And I hope you all have a good night.